Okay, awesome. So the company is called Brytlyt. I'm the founder and the CEO. What's really interesting about what we've done is we've combined graphics processor units and data processing and graphics processor units to deliver speed of thought analytics via Postgres as a front end. I always think with these kinds of presentations, I'm obviously going to dive into the Postgres and the GPU side of things. There's a couple of interesting twists to that tale, but I always find it quite interesting to hear about where it all came from. So as you can probably tell, or possibly tell from my accent, I'm actually from South Africa, and I did a BSc in engineering at the University of Cape Town. So if you've ever been to Cape Town, it's a beautiful place. There's a big mountain, and you can see that on the left-hand side. That's our campus. I used to play rugby on those fields, and I stayed in the building in the front and on the right. There's a quad right in the middle, but on the front and the right. And that's where I went to university. Beautiful place. I was fortunate enough to be given a bursary, a scholarship, to study at Cape Town. There's lots of mining that happens in South Africa, and that's where my bursary came from. And so that meant I needed to go and work on the mines afterwards. And every day I passed a sign like this one. This is Madikwe, a mine, a platinum mine in South Africa. And you can see it says there 8 million fatality-free shifts. And anybody that's celebrating that you didn't die today, any job that celebrates that you actually made it through alive is probably a little bit too adventurous for me. I thought maybe my life was a bit more valuable than that as a work, and so I went into data warehousing and business intelligence, and ended up in the UK. Now, engineering is a great course for me. I'm very curious, and about 8 years ago, 2018, a bit more than that, 10 years ago, 12 years ago now, I came across an article where people had, where a bloke, a Russian guy, had cracked an encryption algorithm using GeForce 8800. And I found that all really, really interesting, that people were using graphics processor units for non-graphic workloads. And this sort of numeric use of GPUs was just emerging. And so I went and got myself this card, the 8800 from eBay, and downloaded the tools to begin programming it. Found it really interesting. But the encryption side was not what I was particularly interested in. And the GPU side, I didn't really have a use case. And then I joined a company called dunnhumby, and they do all the analytics, customer analytics for Tesco's. And at that point, everything came together. So they were making a lot of money, running some really interesting insights. They had some very interesting data sets, very large data sets. But the underlying technology was really struggling to deal with the kind of workloads that it was being asked to deliver. And so I thought, you know what, I bet you GPUs could really help with this. So I spent 18 months researching how one goes about doing that. And essentially what you're researching actually is how to do things in parallel. So GPUs are these fantastic devices. We all know about them now for Bitcoin mining. They're very useful in deep learning as well. But they're fundamentally different from your standard CPU processor. And the reason behind that is they are very parallel in their architecture. So lots of little processing units. Modern GPUs can have several thousand cores. And the whole paradigm is these cores are all processing the same instruction. The only thing that's different is the data. So single instruction, multiple data is the paradigm. And that means that the actual algorithms that you're using to do fairly simple database operations need to be parallelizable. Now, quite a lot of research has been done over the years in sorting and parallelized sorting algorithms. There's some very efficient ones. I'll come onto that later in the deck. Same with aggregating and grouping and so on. But one of the things that is difficult to parallelize efficiently is joining. And when you think about joins and relational databases, the word relational pretty much means join. So you get your tables, which are the relations, and when you bring them together, you use a join. as we all know and love with Postgres. And doing that in parallel is really difficult. And if you can't do it in parallel, then you can't use GPUs. So I discovered a suite of algorithms that allowed me to do this in an efficient way. And that was the start, which brings us to today. So Brytlyt is the fastest and most advanced GPU database on the market today. And our mission is to empower organizations to deliver transformational data analytics. And the key to this is speed of thought analytics at scale. We're recognized independently, third parties have benchmarked us along with the benchmarking we've done, but we're recognized as the world's fastest database. We've invested 4 years in research and development, so we've been running for about 5 years now altogether. We've got patent pending IP, which I talked about with joins. And our software has gone through a number of iterations. So the fourth generation GPU manager bridges this gap between SQL and AI. And I've got a bit more to talk about on the AI side of things. And the real value is not just the transformational data processing, it's actually how it's packaged up and presented to the market. And a big part of that is that we use Postgres. That's really important. I think also I'd like to just pause here for a moment and say a couple of things about the present day. So we've just closed a round of funding with two tier 1 VCs in London and in Amsterdam for £3.2 million. With no changes to our term sheets. We closed on time as expected. We initially started speaking to these investors before COVID-19. And so I think it's a great validation of where we are and what investors are thinking of us, that we're able to close that kind of a round of funding and move forward. The announcement, public announcement, will be going up next week or the week after. And so what I'd also like to say is if there's anybody who finds what we're doing interesting and would like to join our team, please get in touch. My contact details are at the end of this presentation. And we are hiring. So we are in the process of interviewing. We offered a role to somebody at the start of last week. They joined, and there's a couple of people who are going to be starting next week. And we still have a number of roles to fill. So please get in touch if you think what we're doing is interesting. A big part of what where our value lies is in our recursive interaction probability. So this is this algorithm, patent pending intellectual property, and it means that we can use the GPUs very efficiently for join operations, and we can also use CPUs. There are 4 other companies that are bringing GPU accelerated databases to market, but we are the only ones with patent pending intellectual property. So let's talk a little bit more about that. So recursive interaction probability, basically you look at your 2 tables with the columns that you're joining on, you sort those columns, and then you chop them up into pieces, say 4 pieces each, and you look at the boundary conditions and see if those pieces are likely to have a join. Likely to, possibly there will either be a 0 likelihood if those the boundary values on those partitions don't match up or don't align, or a non-zero probability that you might get a interaction. And you recursively iterate over that several times until you get to the base case. But the great thing is it's embarrassing parallelizable, which means it's great for GPUs. It's very efficient with a big O notation of n log n. And efficiency is really important because there are other parallelizable algorithms out there. Your standard nested for loop join is also embarrassingly parallelizable. The issue, though, with that is on large data sets, the number of operations or comparisons that need to be executed grow exponentially. So very inefficient on large data sets. You can also use this algorithm to do a search, and that search is very efficient as well with log n. So I mentioned there are other databases. There are 4 other companies taking a GPU database to market. All of them emerged around about 2014 at NVIDIA's big GPU technology conference. So not the gaming conference, but the conference they set up for using GPUs in non-graphic ways. Brytlyt has focused on how to get the most of the GPU, so we're very GPU-centric. Kinetica uses GPUs, but they are more CPU-centric, so they offload from CPU RAM, CPU memory onto GPU to do the processing. And Scream is focusing on how to lift data off storage and onto GPU. The great thing, though, is there are only 4 companies doing this. We're all taking different approaches, which means that we're all sort of not overlapping, which is great. Our approach, being very GPU-centric, means that we are the fastest, but it does mean that we need a lot of GPU power. So there's a very specific niche use case for us within this. We are extending what we can do into the RAM world as well. So in this quarter, we did our quarterly planning. It was a bit delayed. We did it yesterday. We work pretty rigorously according to quarters and do a lot of planning at the front of the quarter. But in this quarter, we've kicked off the process to be able to use more CPU RAM resources for this. Okay, so we see a number of levels of parallelization within the GPU side of things. I do come to Postgres as well. I know this is a Postgres user group, but the GPUs are a big part of us. So let me cover off that first. But yes, we see 4 levels of parallelization. So the GPUs themselves are massively parallel, as I mentioned earlier. When you're coordinating a number of GPUs and the data and coordinating that with CPU, you've got a lot of data streaming on and off the devices. So that is a level of parallelization where you have data going onto the GPU, processing on the GPU, and data coming off, all happening at the same time in parallel. You then have coordinating multiple GPUs and then the machines themselves in a cluster. The bit that I think is interesting as well is on the GPUs, we are very tightly integrated with PyTorch. And that means that we can bridge the gap between the SQL world, which is where data scientists spend the majority of their time. Up to 70% of a data scientist's time is actually wrangling data using SQL, and bridge that with the PyTorch world, where all the sort of more recent AI and ML things are happening. And the reason why we do that is in the deep learning world of PyTorch and Google TensorFlow, the very basic data container data operator is a tensor. It's in the name, Google TensorFlow, right? Now, what a tensor is very simply a list of data. And the other place where you get data structures like that are in tables. Columns and tables are lists of data. So what we have done is we have taken PyTorch or Torch and the way it uses and manages data on GPU, its lists of data, extended that and enhanced that so that we can now use it for columns and tables. And so our columns and our tables on GPU, as far as PyTorch is concerned, are exactly the same. And that means that we can use Postgres to load and manipulate data on GPU very fast, very efficiently on a cluster of GPUs, and then open up a Jupyter notebook, load the PyTorch modules, the Brytlyt module, connect to the database, and cast a PyTorch tensor, or cast the column as a PyTorch tensor without any copy. It's all done via pointers. And while managing pointers on a Linux system, there's a lot of libraries and capability to do that. It's fairly well understood. managing pointers between different processors on CPU and GPU RAM starts to become a little bit more tricky. And so that's one of the things that we're rather proud to have done. So we've got inter-process communication happening between Postgres and the various Postgres processors, PyTorch, Python, and also the various processors that are going to be consuming GPU RAM. So pretty cool stuff, and definitely cutting edge engineering. So some of the things you need to take into account when you start doing this kind of thing. For instance, it's applicable to power. So for IBM, so we've done a lot of benchmarking on IBM. We've got a good relationship with IBM. NUMA architecture obviously also applies to x86 architectures. But basically, to get the most out of the GPUs, one needs to, and data transfers between GPUs, you need to make sure that you are linking the GPU to the right socket. If you don't realize the full potential. So actually, the way we set up a single server is as two independent nodes or clusters. So a single physical machine will actually have two clusters on it, and that configuration or architecture can then be scaled out. We can hook up numerous servers via network, and that's all linked together as a single entity, a federated entity, all those GPUs working in unison against as a single database entity. Which means we end up with fantastic compute capability. We are being used in production with a number of tier 1 telcos. So Verizon started using our product in February last year. They renewed a substantial contract with them. There's a Polish operator that is using our product, Deutsche Telekom, Telefonica, EE, Vodafone. In fact, at the latest count, I think we've got 27 operators across the world using our database platform to interrogate data gathered off phones to understand network performance, user experience, and aggregate things like signal strength, upload download speeds. In fact, there's about 200 measures that come off the phone, and various different radio bands, technologies, and so on. You can even get the OS battery life, handset model, and so on. And so the operators are getting this data and then visualizing it on a map and wanting to drill down and understand how they are performing down at a zip code level or at a state level or at a county level, and how they are performing with regards to the competition. Mark Levinchik is a guy who's done some benchmarking across a number of different database technologies. And for instance, this highlights a comparison between Brytlyt and Spark, which is an in-memory version of Hadoop, essentially. And if you look at the results, Brytlyt is in the region of 1,000 times faster. 1,000 times faster is game changing. It means that stuff that might take hours can be done in seconds. But even if for queries that are taking 5 or 10 minutes, the user experience where you can look at a billion row data set or billions of rows of data, which is what we are doing, and interrogate that in a very responsive, immersive way with millisecond response times is hugely beneficial. It means that analysts and decision makers can dive into data without really knowing the question, but they can go and investigate a problem space very efficiently, very quickly, very completely, and come out with insights that are valuable to the business. Just a little bit more about benchmarking. So TPCH, I'm sure we're all familiar with that. It's one of our favorite benchmarks, but we were running a 2.1 billion rows per second benchmark. TPCH was run, query 6 was run in 20 milliseconds. and that required 360 gig a second data throughput. Considering that Usain Bolt's reaction time is 150 milliseconds, I would call that a real-time response. So it's quick enough to go below human perception. So incredibly fast performance on large data sets. There's another company who changed names, so this deck is fairly old. They used to be called MapD, they're now called OmniSci. This is a benchmark that Mark Litvinchik did. These times are in milliseconds. The data set is 1.1 billion rows of data. So Brytlyt is running sub 10 milliseconds on large aggregations. And that's without indexing. So that's just hitting the raw data. We also looked at a couple of other queries, maybe a bit more complicated. These ones are using indexing with Brytlyt. And so, again, sub Usain Bolt reaction time type performance with those kinds of queries. And this is with 1.1 billion rows. So very impressive performance, even when compared to other GPU databases. Our indexing is here. I'll jump back to those slides. But basically, the way we do indexing is is useful when we're looking at group bys. So there's two things about our indexing. First of all, a lot of what we do, the main workload happens in sorting. So to do a group by, we actually do a lot of sorting first. Sorting is the most expensive part of that operation. It takes up about 90% of the runtime. And if you can have your data pre-sorted, you get 90% of your runtime back. So massive improvement in performance for these kinds of queries. And you can you can create an index on a single column, or you could use a covering index over a number of columns. The index is really actually just a permutation of the data in its ordered state. So whether we have just a single column or a number of columns in our index, the storage of that is actually very light and the same size, which is not typical of what one would have in other databases. Typically, index is a new copy of the data. Just wanted to jump back onto the sorting. So Bitonic Sort and Radix Sort are two sorting algorithms that are parallelizable and therefore very efficient on GPU. So these are the sorting algorithms we use. I think Radix Sort is actually the one that we're using at the moment. And that's because it's been implemented in a library called Thrust, which we use on the GPUs. How does it fit into the data space? So if you look at data, how old it is and how relevant it is, products like Hadoop can go and capture and store a lot of data. And that means you can create stuff, store stuff is old and not necessarily that relevant. But the stuff that's really high value is the stuff that's highly relevant and recent, and that's where Brytlyt fits in. And then products like Greenplum, another Postgres clone, sort of sit in between that. So maybe not typically used at the scale of Hadoop, but not able to deliver quite the performance that Brytlyt is able to deliver. A little bit about Postgres. So, Brytlyt's all about using GPUs, and its birth was out of my research and using GPUs to do joins specifically. And once I had that little nugget, the next bit was to try and work out how we turn that into something useful for the end user. An algorithm by itself, even an algorithm running on GPUs, is not that useful. And I spent a bit of time researching what kind of platforms or databases we could wrap it up in. I even at some point considered writing my own database and did a course via Coursera on compilers and all that kind of stuff, and pretty quickly realized that that was a monumental task. So I had a look around. One of the first ones that I came across was SQLite. That looked really interesting because its code base is only 10 meg of data, 10 meg, let's say, the actual code base. It's used extensively, and it's open source. So I thought, well, if I'm going to have to dive in and change stuff, it's a great option. The problem, though, is the way the engine is implemented. It's a very monolithic type of construction, which means that it's very difficult to tease apart, and so actually very difficult to insert your own little bits. And so Postgres, I looked at Postgres and very quickly realized that it's ideal for what we were wanting to use, and was able to dive in and get it working in a fairly rudimentary way with sorting pretty quickly. So what do we get from Postgres? Well, the main thing that we get is the parser, the optimizer, and the executor. So the user enters their command, gets passed and goes to the plan and optimize it, and then out comes an execution plan. And up to that point of the execution plan, we just use standard Postgres. It's at the point that the execution plan then starts getting executed by the executor that we hop in. And so we sit there and monitor the nodes and the edges of that tree structure. We still are able to use standard Postgres storage. The GPUs appear as foreign data wrappers, as foreign data tables, and I've got a slide on the architecture in a moment. And so when that plan gets to the executor, we look at what the operation is. So is it a hash join or right join or index or a table scan or whatever it is? We look at what the relation is. Is it a standard Postgres relation table, or is it one of our GPU tables, or is it another foreign data table, foreign table? If it's one of our GPUs tables, then we say, hang on, okay, leave it to us. What is it that you want to do? What is the operation? So it might be a scan, aggregation, a sort, a join. We reach out of the Postgres process, send an instruction to our GPU manager. GPU manager coordinates all the GPUs across the cluster, manages that, understands what needs to be done, tells the GPUs what needs to be done, sends whatever data needs to go to the data, collects any results from the GPUs themselves, maybe does some post-processing of the data that comes off the GPUs, and returns that to the Postgres executor, which then goes to the next stage of its execution plan, and the whole thing is repeated. You know, is that a GPU table? Yes. Is it data on GPU? Yes. Okay. Leave it to us. We'll go and do it and tell you when we're done. And eventually you get to the end of the process. It is possible to write your own SQL parser. There's a great book from O'Reilly that uses Flex and Bison, which is exactly what Postgres uses. So if you'd like to build your own Postgres parser, your own SQL parser, there's a guide how to do it step by step. It's a huge process, and we feel that it's best done by the experts, and Postgres has already achieved a huge amount with that. So this is what it looks like graphically, the architecture. We started off with Postgres 9.4. We then did an implementation with Postgres XC. Let me just check that. Yes, XC, that's right. And that provided us for a period of time with the MPP capability to run on a cluster. So each GPU, if you're familiar with Postgres XC, It has a data node and a coordinator. Coordinator manages everything. The data nodes have the data themselves. So each GPU was a data node. There are some limitations there. So PostgreSQL doesn't deal with things like count distinct very well, and a number of other things. Some joins, some data redistribution. So we then went back to Postgres 9.4, but this time we implemented our own way of managing how things like count distinct and the GPUs all worked. So that's where we are today. And actually, we're no longer on Postgres 9.4 either. So as of this month in April, all of our environments in production with the operators, so the 26 telco operators that are using our product at the moment, are all running on Postgres 12. We spent 6 months, the last 6 months, migrating from Postgres 9.4 to Postgres 12. We resolved, it gave us a great opportunity to resolve a ton of tech debt, and we reviewed our GPU manager. But essentially what we have is Postgres in blue on the left. User sends their instruction to the parser. Parser looks at the grammar and everything, creates a form of an execution plan with the planner. Planner does a bit of optimizing and then hands an execution plan over to the DB engine. And we then have our tentacles into the DB engine, our listeners, and work out when and where we need to actually say we'll take over a particular operation. The GPU manager does that, managing the hardware, GPU hardware, and we rely heavily on foreign data wrappers, actually. So the GPU tables are foreign tables as far as Postgres is concerned. When we do DDL, data definition language, create table, drop table, all those kinds of things, we use standard foreign data wrapper type mechanisms within Postgres. Loading data is also used via that mechanism, and it's a great feature within Postgres because it allows us to connect to all sorts of other third-party data sources. I know we said there were questions at the end, so you know, if you've got any questions about this, take note and we can come back to that. So what does it look like altogether, the entire stack? So in orange, we've got the Brytlyt technology, which is basically Postgres with our API integrated into Postgres. We can scale out, we can use GPUs and we can use CPUs. Because of the foreign data wrapper, we can integrate with a bunch of other data sources, MySQL, Mongo, Oracle, all sorts. There's actually, I think, about 60 foreign data wrappers out there today in various states of development and maintenance. But it's a great attribute and a key part of getting data into the platform. And then in blue, we've got the various tools that you can use to interact with the Brytlyt platform. Obviously, Postgres. So we use all the Postgres tools every day, either to manage clusters for users to connect to the database. So Postgres, pgadmin, PSQL, Torch, Python. Torch and PyTorch and Jupyter are mechanisms to run AI workloads on data that was originally created and managed by Postgres. Any of the visualization tools like Tableau, Power BI, MicroStrategy, they've all got Postgres connectors. So they will all work out the box with Brytlyt. And we also have our own visualization tool called Spotlight. It's got very sophisticated geospatial capabilities, mapping, being able to plot points on a map, do polygons on a map, and use that in a very sophisticated way. Browser-based and relies on Plotly for the charting capabilities. Very cool tool. A little bit about joins. So, you know, joins is the foundation of relational databases. It's a defining feature and a really valuable component to it. This is the TPCH dataset and the various joins and keys that one can run on that. So this is really just to highlight the recursive interaction probability algorithm and the ability to run that in parallel on GPUs for very, very fast joining. And so finally, I'm just going to run through the 3 products that we have. So we've got the Brytlyt database, GPU accelerated Postgres. Brytlyt is the only of the 4 GPU vendors. Brytlyt is the only one to be looking and using open source database technology. So everybody else is developing their own databases from scratch. Developing a database from scratch is an incredibly complex task. Takes a lot of time, it takes a lot of money, and we are very pleased and fortunate that we have chosen Postgres to start off with. It does mean that we had to spend a lot of time in research and development, understanding Postgres and understanding the GPUs and how to get them working together efficiently. But after having migrated from 9.4 to 12, we are able to add in new capabilities very quickly. So for instance, there's a whole suite of windowing functions within Postgres and lots more. There's geospatial capabilities. All of that is available to us to hook up. And whereas the other vendors got out of the blocks very quickly with some very interesting products, if you look at how they've moved in the last 18 months, you'll see that their progress has actually slowed down considerably, and ours is accelerating. And that's all to do with using Postgres. We have Spotlight, so a very cool visualization tool, browser-based. Start off with a blank canvas, and then you can add on all sorts of charts, line charts, pie charts, bar charts, all connecting to the database. It does stand on its own, so you can use any database as the underlying data platform, but it works really well in conjunction with the Brytlyt DB. And then the last thing is BrightMind. So by using the same underlying source code that Torch uses to manage data on GPUs, and using that for the columns in tables, we are able to bring together all in one space, all on GPU with that tremendous performance, the SQL world with Postgres, the AI world with PyTorch, and the speed of GPU. And that's the end of my presentation. Those are my contact details, so if you're interested in finding out more, then please drop me an email. I'm happy to take any questions.
Thank you, Richard. Do you have any questions? Please feel free, like, to unmute yourself or just type on the chat.
Okay, hi. First of all, thank you for the great talk. Can you hear me well?
Yes, if you could up your volume a little bit, but I can hear you fairly clearly.
Okay, I will try to talk louder.
Okay.
Unfortunately, just a laptop microphone.
Okay, no problem.
Sorry for that. So my first question is, you mentioned that you're using foreign data wrappers and that you differentiate between GPU-backed tables and regular PostgreSQL tables. And my question is, how does that work with storage? As in, is the data on the GPU-backed tables actually stored like normal Postgres tables and then just copied to the GPU for specific execution plans? And the question is, how does that map with multi-version concurrency in PostgreSQL? And in general, does the data live on the GPU or is copied there, or is a subset copied to execute the query?
That's a brilliant question. It's a really good question. And there's some fundamental bits there that are really important. So the first answer is, and you've asked a couple of questions there. The first answer is the data is stored on GPU. So what you do when you say create foreign table using the GPU server, foreign data wrapper server, at the point that the data starts getting inserted, it goes straight to the GPUs, and the GPU memory is allocated, and it sits there. There's no data in storage. So that means a couple of things. The first is if you turn the machine off and turn it back on again, your data won't be there anymore. Okay, so you'll have to load it again. The second thing is Brytlyt is an analytics engine. It's not, GPUs aren't very good at doing transactional workloads. They're good at doing lots of things at the same time, but a transactional workload where you've got one transaction and a couple of rows that need to be locked and then updated and then released, and your concurrency and your version controls, all your ACID compliant type of constraints, we don't try and meet that. So it's very much an analytic workload rather than a transactional one. Why do we do that? Okay, so one reason is GPUs aren't good at doing transactions. The second thing is, why do we store it on GPU? Because that's quite an expensive way of doing things. Now, there's a couple of different approaches to using GPUs. But fundamentally, if you look at the architecture, the hardware performance of the different architectures, if you look at GPU RAM, modern GPUs can read data at about 1 terabyte a second, which is incredible, right? You can get server chassis that can put 16 GPUs into a single server. So you've now got a machine that can read data at 16 terabytes a second. Not 16 terabytes altogether. You're probably going to have, maybe half a terabyte, but you can read that data at 16 terabytes a second. If you look at the host machine, which is the CPU RAM, that memory, typically high-speed memory today in servers is about 100 gig. Okay, so you now got a system where data I/O, and in databases it's I/O that is the constraints. The typical operation is a comparison. If you're sorting, at least in analytics, if you're sorting or joining or grouping or whatever, it's a comparison, very cheap. So data I/O is a problem. 100 gig on the CPU, 16 terabytes on a set of GPUs, so it's 160 times faster, just I/O wise. So even if you wanted to read data off CPU, and you could get it onto GPU as fast as the CPU could read it, you're not going to be able to keep up with the GPUs, because the GPUs are going to be 160 times faster, right? So they're just going to be sitting there waiting for data, even though it's coming off CPU RAM as fast as it can. The additional constraint, though, which is significant, is the CPUs are connected to the GPUs via the PCIe bus. So all the data has to go over the PCIe bus, and that is typically around 20 gig, maybe 30 gig, depending on what generation of PCIe. Plus that bus needs to be shared across all the GPUs. So each GPU is probably going to get a piece of that. And that's a severe constraint. So even though you can read it out of CPU RAM, it slows down going across the PCIe bus. It ends up in GPU, and GPU just laps it up really, really quickly. So if you want to get the most out of the GPUs, the data needs to live on the GPUs, because getting it on and off is really, really slow. And then the same thing with disk. You got exactly the same kinds of problems, except for disk there is really, really slow. Now, different vendors are taking different approaches, because there's a trade-off, right? So the trade-off is small GPUs, or GPUs are relatively small, therefore the data set is typically smaller. They're pretty substantial, so we could fit up to half a terabyte of RAM of data without too much of a problem. So the trade-off is relatively smaller data sets, but still big on GPU. Much bigger data sets that are resident in CPU, but then it looks more like a CPU in-memory database, or much larger data sets on disk, but then it looks like a traditional disk database. And the CPUs aren't, the GPUs aren't really brought into their full, the full potential. There are some Postgres, so there's at least one Postgres GPU solution out there called PG Strom, that's an extension, and it relies on transferring data to the GPUs. Basically, the planner or the optimizer actually looks at the instruction and does a quick sort of calculation on what is the time it's going to take to execute this on CPU, traditionally, the disk and CPU, compared to moving it across the PCIe bus, crunching it on GPU and bringing it back again. Now, some things like geospatial workloads might be computationally more expensive, and then that kind of a thing makes sense. But it's not going to be as fast as GPU itself. Does that make sense?
Absolutely.
Cool. Having said all that, a lot of our customers want to have the bulk of that data readily accessible in memory. So we've got our focus this quarter. We've done a lot of the preliminary work, and it's been on our backlog for a while. But the focus this quarter is what we call level 3, which is all about streaming data from CPU RAM onto GPU, aggressively indexing it. So just the data that we need to lift out of CPU RAM is lifted and transferred to GPU for the final crunching. And we're going to apply that approach all the way through to disk resources as well.
Okay. There are some questions in the chat. Tom is asking if there is any option on Swarm 64.
So Swarm 64 is an interesting thing. I knew somebody who worked there. My understanding of what Swarm 64 is they also using Postgres, and they're using FPGAs. Using Postgres in this way is not trivial. It requires a huge amount of research and development, literally 4 years. So it's taking us a long time to get to a place where it's usable, stable, can do numerous operations, can do the joins, can do the aggregations, and do it in a maintainable way. One of the first things we had to overcome was the fact that the very first implementation, the GPUs were the GPU code was actually part of the Postgres process. And as soon as a new session was started, a new process was spawned, and all the GPU stuff was left behind in the parent process. So we could only run with one user running one query, right? So you've got to overcome all sorts of things like that, and understand the various ways that the execution plan is formed and created. So the Swarm 64 guys are on the right track. They're doing the right thing, but they've still got a while to go. And their development roadmap is doubly challenging, because doing stuff on FPGAs is really difficult. Doing stuff on GPUs is quite difficult, but there's a lot of libraries that abstract away all that complexity, and it's a lot. It eventually becomes a lot like just writing standard C++ or C code. When you're writing for FPGAs, you've got a whole additional level of complexity in trying to actually write the FPGA stuff. And the interesting thing there, intuitively, this is my opinion, FPGAs are brilliant at doing a very specific workload very efficiently. But databases need to do all sorts of different workloads. They need to do joins, they need to do sorting, they need to evaluate expressions, aggregations. So you need to add more and more flexibility, more and more different things that the FPGA needs to be able to do to fulfill those database operations. And actually, you get to constructing something that's more and more generic, which means you're giving up more and more of the intent of an FPGA for an FPGA, and it moves into more and more of a more generic type device like a GPU or a CPU. So I think the Swarm 64 guys, it's a very interesting project. I think they've made great progress. It's great that they're using Postgres, but I think they've got quite a long development cycle ahead of them. Okay.
There's another one from MacBook. he said that you met at the MariaDB event in New York.
Cool, yes.
How do you compare with some of the products in that market?
In the MariaDB market? I imagine I can't see the...
Yeah, could you specify MacBook, please? Yes.
Yeah, so at that presentation, what we did was we integrated our GPU manager with MariaDB and got some queries running, within a month we had integrated, which I think, first of all, demonstrates how useful the GPU API is, and also, the MariaDB side of things. We had a conversation running with MariaDB, but that sort of has gone a bit quiet recently. It's difficult as a startup, so we've got 14 guys, we're hiring, we've got a bunch of money, and we're growing, but it's difficult to maintain two different versions of the software, one in Postgres and one in MariaDB. So we've had to sort of take a bit of a choice, make a bit of a decision, focus in on one. Postgres is very well suited to this kind of thing. There's lots of very successful, if you look at the databases that are successful out there, Redshift, Greenplum, Citrus, and Netezza, all Postgres clones. If you get it right, it's successful, but not everybody is doing it. So we don't have a heavy focus on MariaDB at the moment. We know we can do it. We've got a bit of a relationship there. I think it's probably something that we'll be revisiting in due course. But at the moment, it's not an active project on our side.
Okay. Tom just mentioned that Swarm 64 just released a non-FPGA solution.
Oh, interesting. That's interesting. That makes sense.
Okay. So, Adam, you want to ask your question?
Sure. So you described your workloads and how the storage works on your side. So my question is, you mentioned forking off Postgres 9.4 then 12, and the way you describe your workload, you would probably benefit more from columnar storage or something like ZStore or forking off timescale DB. So the question is, are you actually using the same data representation on GPU as PostgreSQL is using, or do you have a custom format that you are mapping with the query set?
Yeah, no, exactly. So that's a good point. Exactly, it's a columnar type approach that we've taken, and we're using Torch. So PyTorch, and the underlying Torch data storage is what we're using. So it's not our column storage is not from the database world. It's from the machine learning world, which is quite interesting. It's quite cool, and that opens up a door for us into machine learning, so that you can use Postgres to do your data, all your SQL workloads, and then open up Jupyter notebooks, load a PyTorch module, a Brytlyt module, and actually interact with the column as if it was a tensor. So there's some very cool stuff that we've been doing there. But you're right, it's a columnar approach. We're not using Postgres storage, and we're not using other columnar databases either.
And in that case, how are you handling row visibility? Because
so basically, what happens is we have the data, but there's basically a permutation index as well, and a permutation which has a list of is basically row numbers, right? So if you wanted a specific row, that permutation would say, okay, I can go and get you these rows. I can get you the elements out of each of those columns for this row, right? Okay. If we want to do some sorting, then or whatever, then we basically always reference that permutation. So if we wanted to say, okay, I'm going to sort on a specific column, So I'd sort that column. I'd get a new permutation, which is basically all my row IDs jumbled up now, right? So when it goes in, my permutation is for row ID is 1, 2, 3, 4, 5, blah, 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 up to 1 billion or 1 million or whatever. If I sort it, then my row IDs are going to be all over the place, right? But they're going to be in the order to sort my data sets according to that column or a number of columns, right? I could sort on a number of columns. And so if I then wanted to say, okay, what is the third row after I've done my sorting? I go look at this permutation, look at the third element in my permutation. It's row 671. Okay, I'm going to pick out all the elements from my columns 671. That'll bring back my row. Does that make sense?
Yes, but maybe I phrased the question wrongly. Like the question is, if I have 2 sessions inserting data, and some data is not yet committed, and I start a computation, then part of the data set is transactionally not yet visible. So you mentioned that you're not trying to be ACID compliant, so I assume that's the case. But I was wondering if you are doing any kind of like multiversion concurrency in trying to differentiate what rows have been already seen by a session or not, or are you always working on the whole data set in such table?
We're very dirty, so we don't do any version control or session control. We are marginally saved by the fact that you can't run multiple processes on the GPU at the same time. So you can only actually run, one process on the GPU. Different processors can call the GPU. So graphics can call the GPU, and you might be running workloads. But I don't know if you've ever used the GPU. If you've done development with GPUs, you can't actually use it for a monitor at the same time, and you can't debug on it at the same time. So you can only run one process. So each session each query ends up with its own session. So if there's a data insert, it'll get queued. And you might have a bunch of queries before it, but they are run consecutively. You then get a data insert. Because of the way the hardware works, while that data is being inserted, you can't run any more queries, and then your queue will back up and you'll get those. So that's just what happens because of the hardware. We don't try at the moment to try and say, okay, this query started at a specific point in time, and therefore the data that it reads needs to be relevant for that point of time. It's all mixed up. But the way the product gets used at the moment is there's a data load once a week, so over the weekend. So we haven't hit that problem yet. We do have some streaming workloads recently in relation to COVID-19, where because some of the data we get, some of the data we're working with comes off mobile phones in real time. There are agencies who want to see that data immediately on a map. So that's a streaming workload, but then it comes in and that queuing mechanism sort of protects us, but it isn't transactionally important. And in the analytics, when you've got billions of rows of data, a couple of hundred rows is not going to shift the numbers massively. So we're lucky in that respect, and we're probably not going to be trying to get more accurate or more granular with our compliance there.
Okay, there is another question from MacBook. How it works in a virtualized environment, like if you've got like a server with several users in VMs?
Yeah, so we actually use a lot of Docker. Everything's deployed via Docker, and the reason why that is, with all sorts of different OSs and libraries, we lean on a lot of third-party code. That can be very difficult to manage in an install. So the database itself is in a Docker container. The GPU manager is in a Docker container, the hub. Each of the GPUs, I understand, they themselves are in containers. So we use a very virtualized approach anyway to try and manage the complexity of different OSs and different libraries and versioning, all that kind of stuff. And so, if we can run all of that at the same time on the same GPU. So you could have multiple versions, multiple instances of the database running on the same machine on the same GPUs. They would each take on a specific set of memory from each of the GPUs. So one would need to understand that. They wouldn't share memory. They each, are allocated their own specific piece of memory, and they operate and run in isolation. So they don't know that there are other virtual instances on the same hardware. Multiple users can connect to each one of those and run their queries. They all get queued. Ultimately, they get queued when they start getting run on GPU. Does that answer that question?
Yes, the answer is yes, and Megbut would like to follow up, to get further details about that.
Yeah, sure, absolutely. You're welcome. I'm not going anywhere.
Okay, Adam?
Yeah, I actually forgot my question, so please go on, and it might get back to me. So
sure. Maybe I've spent a bit too long answering those questions.
Okay, there's another one from Philip. So Philip, please go ahead. Oh, he just left? Oh, that's okay. And joined again. Okay, so Philip, if you...
Excuse me, yes.
If you...
Yes, Richard, just two questions, because I was joining quite late, so maybe I missed some details, but the first question is, are there any benchmarks available except from those visible on Mark Litwinczyk page? Because when you search for Brytlyt DB performance or benchmarks, it is the only actual page that pops out.
It's the only one that... Go on. Sorry, second question. Go on, Philip.
Yeah, just the second question before you answer. So the second question is there any downloadable version of the product which could be tested offsite? Yeah.
Two very good questions. Okay, so yes, Mark Litwinczyk is the only publicly available benchmarking that we've done so far. It's quite old, actually. It's 2 years old. So, Philip, you probably will have missed the bit where I was talking about us recently closing a round of funding. So we've got our Series A, 3 million, 3.2 million in the bank. It's publicly announced next week or the week after. But part of that process was a whole series of due diligence and benchmarking that we did on our latest versions of software. Significant improvements on the last version. And we are working through how to make that available publicly. There are some complexities with doing that. So while Mark was given authority by OmniSci to publish their results, the OmniSci previously MapD license prohibits you from publicly doing any revealing any benchmarking that you've done, understandably. So we did that benchmarking, but we can't, and you could do that benchmarking as well in the same way that we did, but you can't talk about it. We can't publish it. So the answer to that is we have done some recent benchmarking, and we're going to be publishing it in due course, hopefully in the next couple of weeks. So keep an eye open for that. Yes, you can absolutely get access to the software. If you could get in touch with me, I can set that up. We can give you access to our, and that goes for anybody on the call. We can give you access to our Docker images, and you can give it a go. We were on AWS a while ago. We've taken that down. Brytlyt 4, which is a Postgres 12 migration, is being used by our customers, and we're going to be releasing that publicly shortly. But the best way to give it a go yourselves is to download it. And we also have cloud infrastructure, our own GPUs, with the latest version of the product running on that. So if you're happy to grab an instance and use that for a period of time to do an evaluation or investigation, reach out and I can make that available to you, no problem.
Adam?
Okay, so I remember my question now. So describing the real-time analytic workload, and especially considering cell phone metrics, the question that I arrive at naturally is, have you tried speeding up or using Postgres queries? Because that seems like a really well GPU accelerated task. Right?
Absolutely. So absolutely. And it is on our backlog. We've done some of the Postgres porting, particularly when looking for point and polygon type workloads. And on our roadmap is to port the entire Postgres set of functions onto Brytlyt. So we'd add in, we'd rename them Brytlyt, whatever, blah, 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 Postgres function, and that would run on GPU. Yeah, very, very useful piece in the geospatial world. And this is the great thing about Postgres, there's all these functions, data types available for us to incorporate into what we're doing and add GPU acceleration to. It's fantastic. We count ourselves very fortunate that all this work has been done already.
Go ahead, Adam.
So I think the next natural question is, considering that you just mentioned the open nature of the product of the project itself, as in PostgreSQL. So my question is, how are you cooperating with upstream development, and has your work resulted in any open source contributions to the project?
We haven't made any open source contributions. It is something that we want to do. We haven't got a relationship running with the upstream people in Postgres. We'd love to work with them, and I can see a lot of reasons why we'd want to. And what we need to do is find a balance between our proprietary work that we've done and the open source part of it. I think what we want to do is release a version of our product in a limited way that maybe runs on just a couple of GPUs or something like that into the community. The open source world is an amazing world, and it provides companies like Brytlyt with a huge amount of resources, and it's very exciting. As a startup, it's very difficult to build a financial model, a commercial model around open source. One needs an extensive user base. It is possible, but it takes a lot of time, and you need a huge amount of adoption. And as a startup with a limited customer base, it's very difficult. So, in the fullness of time, I imagine we would open source more and more of what we've done. But at the moment, we need to realize that that isn't possible. Otherwise, we wouldn't be able to pay our developers.
Thank you for the answer.
Okay. I think there's no other questions. So maybe like the last one from me, if you don't mind, because I've seen that that you've shown like hash joins. Does it makes any difference? It's just nested join, hash join, and merge join. Does your solution supports all of that, or there's any that one is much more efficient or another one?
So when absolutely. So Postgres supports tape join and a form of merge join. hash join, nested for loop join, and the planner will typically work out what's going to be the most efficient algorithm to use depending on the cost of that algorithm, the data set, and what needs to be done when the data comes off storage. For GPUs and the kind of workloads that we're doing, the most efficient join is actually recursive interaction probability, the stuff that I did the research into. So if it's a GPU join, it's going to be a recursive interaction probability join. It's far more efficient and far faster even than hash join, particularly on large joins that might be what I call sparse. So a good way to think about that is contact tracing, which is something that we're looking at the moment. So imagine you're able to capture all the potential contacts that are happening using phones. So people are talking about using Bluetooth. A Bluetooth, the low energy Bluetooth signal can be used to maybe say, okay, these two phones are within 5 meters, 2 meters, whatever of each other. And they've been in that state for 10 minutes. Okay, we'll call that a contact. And you capture all of those all the time, and you end up with this big table that might be billions of rows long. You then have somebody who comes along and gets tested, and they test positive. So you want to work out with this single ID who else they have been in contact with. So that's just a search, right? That's a where clause. But it's a very it's one of those unique sort of things that look a lot like a join as well. So we use recursive interaction probability to go and find it's a join of one, right, to start off with. So on the one table, you've got one element and join it to 1 billion, and you get out, maybe 1,000, maybe a couple of hundred contacts that this person had been in contact with over the last 10 days. You then want to do the second layer of that, those couple of hundred or 1,000 people that they've been in contact with. You want to do that again. So now you've got a join of a couple of hundred to 1 billion, and you maybe get a couple of thousand out, and you want to then process that again so that you can step through the various layers of interaction from the primary to the secondary to the third, right? You understand that. Now, those are all joins, but the number of interactions with the large data set, the billions of rows, is very, very small. And if you use something like hash join, even if you could fit one of the data sets in memory, that billion row data set is going to have to be traversed at some point or another completely to do that hash join. Whereas recursive interaction probability very quickly identifies which parts of those billion rows need to be properly investigated and which can be discarded. So yeah, that's a fuller answer to what was essentially a straightforward question, I think.
Okay, thank you very much. I had no idea about this one. Okay, so maybe the last question from Adam, and then we because it's almost 1.5 hours. So
good, we filled that time up.
Yeah, totally. So I think that if people would have any other question, they can ask you, right? There's contact details posted here. So
no problem.
So sorry for that last drop-in. The quick question is: have you tried or considered accelerating the planner itself, especially in multi-table joins when it tries to incorporate genetic algorithms to pick a plan because of time limits?
That's a good point. So we haven't yet touched the parser or the planner. We have touched it very briefly. There's the copy. We've got our own version of copy so that you can do a table-to-table copy rather than insert into. It was for us, and using GPU tables and being outside of Postgres, insert into didn't work as well. So we've changed. We've added copy to table. Apart from that, no. But it is something that we every now and again we think, sometimes the planner chucks out an execution plan that doesn't work for us very well. And sometimes for the same query, we get one plan and another plan that we need to work with. So absolutely the next stage, probably next year sometime, we're going to start diving into the parser and the planner. Now that's a whole different side of software. Whereas the bit that we're working at the moment, I think, is very easy to understand and touch. When you start talking about parsers and planners and so on, particularly the parser with grammar and so on, it's very abstract, and we'd be touching that, in a with a lot of caution.
Okay.